All right, so welcome to the first lecture for Programming Languages course, CSCI 305. I'm Isaac Griffith. Anyway, so this is the first lecture. It's just an introduction to the whole concept of this course and what's going to be beyond the introduction of the course logistics that happened on the very first day of class. So basically what we're going to do is we are going to go through and look at all these different languages, and more we're trying to understand languages from a specific view on programming. And so what we have to realize is there's an extreme variety of languages right now. As this says, even back in 1995, there was over 2,300 published languages on a news group. If you don't know what that is, that's because, 1995 is like a long time ago, 22 years ago, and I'm dating myself now. It's possibly even older than vast majority of the people in this class. Now, there's what they call families in this. It's also called paradigms. There's typically four major paradigms or families for programming languages that we are concerned with, and those are imperative. So think about, for example, the C language. There's functional, which is we're going to deal with through ML, but other functional languages are Lisp, Scala, OCaml, all these other ones. Logic-based languages like Prolog, as we're going to study. And then there's object-oriented languages, which I'm sure you're familiar with at least one, Java, but if not, then Python. But we also will explore a few other concepts associated with all these things. And so beyond that, right, so that's family. Those cover huge numbers of languages, and some a significant number of languages like Java, Ruby will cross between these different paradigms. But languages also have, they kind of serve a certain set of domains. For example, in scientific computing, still to this day even, Fortran tends to be one of the most widely used languages for scientific computing because of its capability to handle large floating point computations and handles matrix operations and array operations quite well and efficiently. On the other hand, business applications, right, where we're not utilizing, for example, floating point, but instead we have decimal numbers, say, for example, representing money, and we have to deal with reporting and characters. Not such a requirement for example, matrix operations like in scientific computing, but rather we're looking at things where we have large sets of data representing customer information, other information for financial reports. These are the things that, for example, what made COBOL so useful. And then we move into other realms, like a little more specific, for example, AI. Now, it is well conceived that artificial intelligence, the most widely used language for those types of applications is Lisp. I would argue that in today, 2017, that possibly, if we're looking at not just artificial intelligence but machine learning, that Python has really climbed the ropes to reach the pinnacle of that, given its vast number of libraries. But I would say that almost any language can be used for machine learning, artificial intelligence. But Lisp was specifically built for AI, and it's well known. Systems programming, which is down and dirty with things like building an operating system or low-level coding in memory management, things like that, has always been sort of the labor of C or assembly. But when we're talking about programming languages themselves, assembly is not really a programming language. So we want to talk about C, and I'm sure we've all felt that experience. So, but C is very efficient. It's very fast, and it can be, and if it's been programmed well, it just becomes a workhorse. On the other hand, you have web software. So when we are talking about web apps or software as a service, we get into a variety of other languages. Most of these are scripting languages, like, for example, which is not shown here, but We have JavaScript or its derivatives like Dart, TypeScript, CoffeeScript, etc. We have the document markup language, HTML, and all of its specifications, as well as XML, JSON for marking up data itself. We also have there's server-side scripting, which could be JavaScript again, or PHP, or Ruby, or Python actually. So there's you can also use Java to build all these services and servers, as well as C# and ASP.NET. So there's lots of different options available, especially in the web game, and this is how a significant number of languages have started to become multi-domain and multi-paradigm. But shifting back, I wanted to put that out there so you can see that a lot of these languages are a little more widely used for certain domains. So when we are talking about these remember we're talking about four main paradigms. So imperative is the first one, and so all these paradigms have specific hallmarks that kind of let us know that that's what we're looking at. And if we look at C's probably one of the most widely known imperative languages. If we want to implement the factorial function, right, simple concept, typically we would do this using recursion, but we can do this easily using a while loop, right? This is one of the hallmarks of imperative languages. There's iteration. Iteration is built in, and the order of the execution of each statement is very, very important when looking at this language, right? Furthermore, we can have multiple assignments. So we have a variable can take on multiple values throughout its lifetime. This is not common in all languages. This is only common to imperative and for the most part, object-oriented languages. So the second is functional languages, and the one we'll be talking about is ML. And so when we want to define this, the factorial function, we simply define the function fact, and it takes value x. And then we just have this recursive definition where if x is less than or equal to 0, then we return 1. Otherwise, we return x times the factorial of x minus 1. Pretty simplistic, right? The hallmarks of these, of almost all functional languages, is variables only have one value. Once they're defined, they maintain that value for the rest of their life. And there's a heavy use of recursion. Some languages, even ML, I believe, have iteration now, but it's, I would say, widely criticized if you do that because you're not programming in the functional way. Another functional language, Lisp, is pretty much the de facto, which we'll talk about in the next lecture on the history of programming languages. Lisp is one of the very first functional languages, and at the same time it is a little more interesting, I would say, given that it has a significant number of parentheses that has irritated people for a long time. But don't let that get it down. Lisp is a very powerful and very useful language. It's functional, but has significant difference in the way it looks from ML, right? Everything in parentheses, basically what it's breaking this down to is into a list-based representation of a parse tree for Lisp. That's what it is. Everything in Lisp is treated as a list, so it's very interesting how it works. But we can see that inside of Lisp there meets all the hallmarks that we expected to find for a functional language. Single value variables, heavy use of recursion. I don't know if you can actually write iteration inside Lisp. It's been a long time since I've written in Lisp, but I'm pretty sure that if you can, it's widely regarded as the wrong way to do things, and recursion should be used instead. On the other hand, we have logic languages. Logic languages are just interesting in the way they actually work, and the way you describe things. It really is more of a description. First thing we do is we basically are describing two different ways of approaching this recursive problem. It's still recursive, but what we're really doing is describing rules logically. And so we have two different rules. In the case that we see that we have some unknown variable x and a 1, if that's our input, then we assign the value 1 to x, right? That's our return value. On the other hand, if we have some x and a value that's not 1, if x, as long as x is greater than 1, we create a new value, new x, assign it to x minus 1, and then our factorial, we calculate the factorial, new x nf, and the commas here are anding, so or conjunction, and fact is x times nf, right? So the interesting thing about this is I think there are a few other logic-based languages, but Prolog is pretty much the most prolific. They are used in a lot of, there's a specific, several different types of AI-based applications and other types of applications where Prolog becomes very useful. For example, there is, in software engineering, we use design patterns to describe microarchitectures and good ways of programming in object-oriented systems. Detecting those, actually detecting design patterns is a very difficult problem, but I have seen an actual implementation for a detector written in Prolog because it describes things using formal logic. Now, we should all be familiar with this last category, object-oriented languages, right? We've all, I'm hoping all of us have started at least in Java or Python. And so object-oriented languages are interesting. These are designed for handling a problem, right? So they all came out, object-oriented languages all came from a more, we'll say, imperative or procedural view of the world. But when those languages, we started having problems that were too large to be handled efficiently, as well as, we'll say, managed by humans, when we're trying to look at large problems like how do we build multiple services or server client-based systems, it gets kind of difficult to do that type of work inside of a language where you're just defining a bunch of functions, as opposed to where you start creating larger modules, which in this case are classes. So we'll look at an example of the factorial in Java, right? So we create a new class called myInt. Basically what we're doing here is we have, it holds an integer value, right? And basically we can get the value of that value. We can also calculate the factorial by calling getFact, which is then creates a new myInteger with the factorial of the given value for the current myInteger, right? And all that's doing is it's going to operate the same while loop based solution that we saw for the C example. And so we can see the roots of the imperative nature inside the object-oriented language, but at the same time we have all this extra business going on here that creates the objects, right? And so the hallmarks here are it's usually imperative, but as I said, but it also has constructs to help us understand and bundle. What we want to do is we want to put the data with its operations. That's the whole point of this. That's object-oriented. Move the data with its operations. The second we start splitting that out, then we are no longer programming in object-oriented ways, but that I leave that for software engineering to handle. So there's also this concept of strengths and weaknesses, right? So remember we talked about the different domains, right? That using those languages for those domains will be considered a strength. Using other languages for those same domain outside the domain could be potentially seen as a weakness. Whether or not that's true is not the point. The concept here is that we do understand that all languages, it's sort of like the no free lunch theorem from machine learning. All the languages can solve the problems. They're all general purpose languages, but the question becomes, are they going to, some languages solve some problems better than others, and we're going to leave this to you to understand how to do this and make these comparisons. But we can say that functional languages do well on functions similar to the factorial, right? Imperative languages are not as good at that. Logic languages are really bad, and we know that object-oriented, as we saw with the Java example, it adds a whole bunch of extra code to handle a simple thing like calculating the factorial. So it seems like it needs much larger examples. Well, I also borrowed from the Sebasta book, the optional book, this concept of language evaluation criteria. So there's 4 different types of things that we want to talk about when we're talking about language evaluation. We have readability, writability, reliability, and cost. And this is the goal for this is when you're selecting language to work on a project, these are the things that you should be really thinking about, right? Readability, obviously the ease with which programs can be read and understood, right? So depending on the type of program you're writing, maybe if we have to write a huge program, maybe using functional language may not be the best choice. Writability, how easy is it to write and create programs in that language? Reliability, conformance to specification. For example, does the language itself conform to the specification to which it's used? So many languages like Lisp had various different, every different group at one point in time had their own version of Lisp until they finally unified into the common Lisp object system, and then it was standardized. There's been a significant number of variants of Ruby, Java, all which do or do not conform to those specifications. And then finally we have cost, right? The ultimate total cost. What is it going to cost for you to write the program that you need to write in the language that you have selected? And all these things must be considered, especially when we're working on a project. Readability, basically we can break it down into 4 different things, simplicity, orthogonality, data types, syntax considerations. The simplicity, basically, is the language easy to use, easy to write, right? We're asking ourselves, it gets more and more difficult to understand what's going on and to read what's going on if we can consistently overload the operators. For example, in C++, you can overload the plus, minus, divide, all the different operators that you normally, the left shift, right shift operators that you normally would think of associated with, for example, strings or numbers, but in C++, I can write code that allows me to, for any object I create, to overload those same operators and apply them to that new object. But the problem becomes, unless someone's aware of that I did that and what that means, they may misunderstand what's going on. And so that's an issue. Although, some languages like Groovy and Scala, which are derivatives of Java, allow you to do that, and in my opinion, it seems to be working. That was a consideration that Java chose not to allow. They didn't want operator overloading because it's difficult to understand what's going on. Orthogonality. Basically, we have the goal is that you want to have a small set of primitive constructs which can easily be combined in a small number of ways, right? Such that every possible combination is legal. That's what orthogonality is all about. Keeping that in mind, I would say that there is in C++ a significant number of possible integer and or data types in general, which are based on whether or not it's signed, unsigned, is it an int, a uint, etc. There's all these different constructs that can be combined to form a significant number of different types. Whether or not that's good or bad, I'm not saying anything. It is orthogonal. There's a small number of them, but there's a significant number of possible primitive constructs. What really matters here is that it's not that there's how many of these primitive constructs there are, but really whether or not there's any possible combinations that are not legal. The second you start having all these little rules, it becomes hard to understand or read what's going on because you don't know which ones are going to be possibly denied. And then that moves us to data types, right? we want the data types to be predefined. We don't want, and that means that the basic constructs are predefined, right? We always want to be able to add our own data types, but having a unknown, what is it? Basic constructs like numbers, strings, characters, etc. Those aren't defined for us. We don't in Boolean types. Those are not defined. Then how can we actually say anything about that? And how can we and how does that affect the readability of the code? Syntax considerations, right? How do we define identifiers? All that stuff obviously makes sense. There should be some rules for that, and it should be flexible, but at the same time simple to read. And APL, a language that does not follow this, which we will see an example of shortly here. Finally, we also want meaningful and keywords, and as well as self-descriptive constructs. Makes very good sense. Writability goes back. We also have, now we have simplicity and orthogonality, right? Few constructs, small number of primitives, all things I've been talking about. For readability, also apply to writability. Support for abstraction. If we can't make abstraction, we cannot make more complex structures. Then we have a problem with being able to write anything of usefulness or meaning, right? This gets into expressivity as well. We need to have, I would say convenient, but also efficient ways of specifying operations that we need. And as well as we need to have a significant number of predefined functions, right? If you don't have like for example in C, there's a significant number of things that, for example, data structures that should be already defined in the language but are not. And so it had led to, eventually the development of the standard library, but a significant number of people implementing the same thing over and over, which then made the writability, there's high writability, but at the same time it was very difficult to be sure about the efficiency of the language, as well as decrease the cost, which we'll talk about shortly here. Reliability. So this is pretty simple, right? We want type checking, exception handling, aliasing, readability, and writability, right? Why we want type checking? Just because it can either be dynamic type checking at runtime, or it can be static type checking. It doesn't really matter, but it needs to have the capability to check the type. That way, we know that of your data, of your variables, such that we can detect when errors have occurred. Exception handling, right? We want to be able to take corrective measures at runtime when problems arise. Furthermore, aliasing, we want to have multiple references for the same location. That makes sense, right? And then readability and writability, as we've already said, there's we want to be able to express, and this gets into our ability to express a solution to a problem, specifically a solution being an algorithm. Without having to go into weird workarounds that are, or what they would call an unnatural to the language approach to solving the problem, right? And then finally get into the cost, right? This is what the cost basically breaks down into. The time it takes to train programmers to use the language, the time it takes to write the programs, the time it takes to compile, the time it takes to execute, and whether or not, and then the actual cost. So time all transfers into money, and then the actual cost of the language system, which we will talk about language systems down the road here. Reliability, if it constantly fails, that actually leads to not only high cost of having to rerun the program over and over, but it also loses customers. And then finally, what is the cost in maintenance? 80% of the cost of a program is maintenance. So if it's hard to maintain, read and write the code, then it's going to be extremely costly to maintain. So there's some other ones that I'm not going to get too deep into. Portability, whether or not you can move the program that once you've written it into different operating systems, different hardware. How general is it? How useful is it to a wide range of applications, right? And then well-defined specifications. Yeah, we'll move on. Finally, we return. So now, getting past that aside on evaluating languages, we return to the original four families. So we had four families, right? Imperative, functional, logic, and object-oriented. But now we have, in today's world, I don't think we really have many languages that don't have at least two, if not three of those things going on. But there's other families that are useful. I've looked into this several times. Depending on who you talk to, there's various different paradigms: declarative, definitional, procedural, event-oriented, event-driven, single assignment, scripting, concurrent. There's a whole bunch of different ones. These languages are all designed for different things initially, and then that creates possibly new paradigms. Even more important is that there are multi-paradigm languages, including JavaScript, as mentioned earlier. There's things like functional, object-oriented, using an odd form of object orientation called prototype-based object orientation. And at the same time, it also is a scripting language. It's procedural, and it's also imperative. So it's all sorts of stuff. OCaml is a ML derivative that, so it's functional, but at the same time has object-oriented capabilities built into it. Lisp has object-oriented capabilities built into it. Python has a lot of stuff from functional, it has object-oriented, it's procedural, it's a scripting language. Then you have Ruby, which we'll be talking about actually. Ruby is a scripting language mixed with everything in it is an object, so it's a purely object-oriented language, but has this capability to be also imperative. And then it has some functional constructs. So there's all these different things going on, and there's no possibility. And really, we just have to understand that there's no specific family for any given one language. Even Java has functional constructs now. If you look under the hood, they're not really functional, but at the high level of actually implementing code in the language, they effectively are. And so we have all these different constructs. Well, and so no one language, but what is their main paradigm? And that's what we're going to be looking at. I'm not going to get into this. Fourth is another language that's odd. It's kind of outside the domain. It's a stack-oriented language, but it's also kind of imperative. But this is how you would write factorial in it. I've never used fourth personally, but I look at it and I'm thinking I probably will never use that. APL. This is the one I was talking about earlier. That is. APL has a special keyboard actually that you have to use because it uses characters to describe things which are not actually on the keyboard. They're non-typable characters. And so, but it's a really interesting language that is based on matrix and vector-based approach to handling for handling mathematical calculations. It was probably pretty ingenious at the time, except for the fact that you had to have a special keyboard, special hardware to actually program in it, which made it lose a significant number or not have a market share in the world of languages. So then we get into this concept, this odd controversies, right? So if you start talking to people about programming languages and which one you're using. For example, I've been using Java since the late 90s, and I like Java, and I don't like Java like I like food, but I think Java is an interesting language. It's a workhorse. It does the job, and so if you start saying things like that to people, you get all sorts of arguments. And in reality, it doesn't matter. Who cares what language you like? I know. And most of the time I get these arguments from people who are super big fans of functional languages like Haskell. Well, that's great. Haskell does the job, ML does the job, Ruby does the job, Python does the job, Java does the job. It doesn't really matter. It depends on what you're trying to get done. That's what matters. Programming languages are tools. But you still find all these heated arguments. And they all have their reasons. And it doesn't matter. But they get into partisan arguments. That's the one that we just talked about. Then there's inside of a given language, there are arguments about the standard and how do we define it and what does it mean, and then what are the underlying fundamental definitions, and it gets really angry really quickly. And so, like I said, arguing about the relative merits of languages, you got detractors, etc. It's almost like religion in a sense, versus atheism, and who's wrong and who's right. Who cares at this point in time? When we talk about programming languages, we are talking about whether or not something is the right tool for the job. That's what we're doing. When it comes to language standards, I do like this because they talk about the Fortran. Right, Fortran has had so many different. So if we go down all the way down here, right, I will put this out. Another one similar to Fortran, which is the example in this slide, is JavaScript. JavaScript stagnated for a real long time. JavaScript is actually, its standard is called ECMAScript, ECMA. It's the European. It's a European. Basically, it's like the ISO standard, but only for European, or NIST in the United States, which is the National Institute for Standards and Technology. ECMA standardized JavaScript, and they as ECMAScript, and it went from like 1.0 to 1.1, and then 1.2, 1.3, and then it got up to 1.5, and then for like a decade, nothing happened. And finally now it's at, then went to, they turned into ES5, ES6, and now I think they're naming them 2016, 2017. So it's actually going much faster now because they've gotten it down to where they've made a decision that they need to get a new release out every for the standard every year. But Fortran, the Fortran stagnation occurred. It was like in 1982. It was actually, I think it was in 83. They actually got 82 done, and then they were going to do they had another one that they abandoned, and then they got 88. Which was actually done, I think, in 89, and then 90 came out in 91. And so, and I could be dead wrong about that, but the Fortran one is just as bad as C. C has all sorts of issues with its standards, and then getting people to be compliant with that, like compiler manufacturers and things like that. It's a nasty business. This concept of basic definitions is really interesting, because then we get into issues like, is it really an object or I really think this is interesting, because when you start dealing with fuzzy concepts and language family names, the more interesting one I think is where where we talk about if they're fuzzy or not. Bad, is X really an object-oriented language? I see this one all the time when people are talking about like JavaScript. Is it really object-oriented? Well, it's sort of object-oriented, but it depends on what you call object-oriented. If you limit yourself down to viewing only things that are class-based objects, like in Java or C#, then no, it's not object-oriented. If we open it up to including the prototype-based object-oriented systems, then yes, of course it is. The question, I really enjoy this because it's saying that what aspects of X support object-oriented style. That's how we should be thinking about things, right? And I do like this. Some crisp concepts have conflicting terminology. One person's argument is another person's actual parameter. I think we need to look more at the way we parameterize things rather than how we argue against things. So programming languages are constantly evolving, right? New languages are always being invented. Old ones developing new dialects. For example, I mentioned earlier, Java. Java's been around since the 90s, right? It's over 20 years old. It's actually encroaching on 30 years old. And this thing has a lot of detractors for reasons that I would say are fairly sound, but that doesn't mean it's a bad language. It has a significant number of libraries implemented. They're all freely available. All of its tooling is essentially freely available. But it has led to implementations on top of it, like Scala. Scala added all sorts of great functionality. It improved the language vastly by including more functional characteristics, tail recursion, as well as the ability to do, I would say, dynamic typing. And at the same time, another language that also grew up around the same time as Scala was Groovy, which is a different dialect of Java. They are both on top of Java, but they compile down to Java, which makes them a different dialect. They just have a different way of describing the same concepts, plus they interact with the language. On the other hand, so new languages give us this really great experience where we can actually start out brand new, don't have to worry about anything. We have no other body of code that we have to worry about, right? So this is always a problem. Whenever you make a change to a programming language, you have to be backwards compatible. This is a problem that happened with Python when they went from 2.7 to 3.0. It broke a lot of things and made stuff no longer work. So that's a danger, and it took a long time for people to shift from 2.7 to 3.0. That being said, there are no languages by themselves are not entirely new. They're using ideas from other ones. For example, when Java came out in the 90s, I mean, it stole everything from a whole bunch of other languages, right? Concurrency, object orientation, the entire structure of how you write the code was basically stolen from C++ and a few other languages. The fact that it uses packages was stolen from Modula. It's really interesting, but it made a brand new language. A problem with creating new languages is that it takes a little while for you to build up the code bases that other languages have, the APIs, so that they can become very useful. For example, I remember when a language that's a derivative of C came out called Rust. It really had to pick up and build up all the underlying libraries it needs to be able to actually compete with other useful languages. And that is sort of why, if you have enough people working, then you can gain the speed and gain the popularity necessary to actually become a widely used language. There's nothing that tells us what's going to become widely used and what's not. So every year there's new languages created, and you never know which one's going to be hot and which one's not. And so that's always a problem as a technologist in selecting new languages. I would just say learn as many as you can, and drop the ones you don't need. But the interesting thing about even languages that are not widely used, for example, a language that came out in 2006, 2007 is called D. It's very similar to C, C++, Java, and C#, and it's just kind of never gained popularity. It has lots of great libraries. It's seemed to have really great syntax and very useful, but it just never picked up. Widely used, Java, right? It's been around since 1995, so it's 22 years old. Like I said, it stole from C++, Mesa for concurrency, Modula for packages, and a bunch of other languages and concepts. But it's extending all these languages, right? It's an improvement upon these and it took and the Java designers actually stated, we're going to take the best ideas from all these other languages and we're going to put together into a single language, as opposed to trying to create new stuff. Almost all these other languages, C++, Modula, ML, Algol, were all creating new concepts when they were implementing the language, right? And Java didn't want to do that. We know what works, that's what we're going to use. There's an interesting language, Algol, which almost every major thing that we have for languages, at least in the imperative and object-oriented world, came from Algol. Unfortunately, it was never used. It was like this great team of what we would call the heroes of computer science, Donald Knuth, Dijkstra, all these several other people. The interesting story was they all grew their beards out and would not shave until Algol 58, I believe, was completed. That took several years. But it did bring in block structure and scope, recursive functions, parameter passing by value, a lot of really good things that we take for granted today. Dialects, as I mentioned, there's all sorts of different dialects. That's how old languages become new. Fortran, as I think, as I said, it's probably still used as the most widely used scientific language. It's been around forever in the world of computing. It's one of the very first programming languages, high-level programming languages. There's code that was written in like the 60s that's still operating, for example, at places like Los Alamos, that was all written in Fortran. There's derivations of Fortran, all from various ones like HPF, Fortran M for parallel processing. That's how supercomputing for highly scientific applications is done. So now we move into programming practice, right? Languages influence programming practice, and programming practice influences language design, right? That's how we went from, for example, in the Java world, why we have Groovy is because people got tired of the way Java operates, right? Every time you need to you create a field in a class, you have to create a getter and a setter. Well, that's annoying. We should just automatically have that. That should just be a part of it. And that actually was one of the things that was introduced in C#, but Groovy, I think, did it in a slightly more interesting way. But that being said, that was issues with the programming experience influenced the language design for Groovy and C#. Whereas the interesting thing is languages also influence programming practice. For example, in Ruby, as we'll see, it's got all the imperative stuff, but the way you write that in the language is dependent on what you're trying to do, and Ruby has its own Ruby-esque way of doing things. Right. So, but Ruby also pushes towards object orientation, although we're not going to use that for that. Functional languages kind of make you want to build all these little tiny little functions that are essentially just a bunch of recursive functions solving a problem. Logic languages, well, we'll get into that, but it's interesting in how it works. You essentially define a database and then you search through that trying to solve a problem. It's quite interesting how it works. There are ways to go against a language, though, and I'm going to show you those. When you start programming in a style not quite what the language expects, or goes against the grain, if you will, it kind of turns out not to be very good looking, or at the same time doesn't meet some of those criteria that we said for language evaluation. So, in fact, we can do imperative ML, which we won't use in here, but it looks nasty. We have this same factorial function, right? I don't know what's going on there, but it is not a fun experience from what I've seen. It was so much cleaner looking, so much easier when it was simply a recursive function. We didn't have to define I and xn with the let keyword in order to use it inside this while loop. Yeah, that's just a dirty looking experience. Same with the non-object-oriented Java. Java, more than C++, as it says here, encourage people to be to adopt the object-oriented mode. Everything you do is defined as a part of a class. Even here, if we want to do non-object-oriented Java, you can define it as part of a class. Now, this does not apply to Java 9. Java 9 actually has the capability to write a script in it. And Groovy does as well, and so does Scala. So you can, and essentially what it's doing when you write those scripts is it is doing exactly what's shown here. It's taking all that code and jamming it into a single public static void main function. It's very annoying, nasty way of programming in Java. It's not going to really work out to your favor, but you can do it. I'm not going to talk too much about Pascal. Pascal is an imperative language and supports recursion. If you were to write it as an imperative using a functional approach, it would sort of look something like this. And what you're basically doing is you're causing a for loop with what appears to be... Oh, yes, you're creating a for loop using a recursive call. It's a very interesting way of doing it. Finally, like we said, programming experience influences language design, which is how we grow these new dialects, right, and potentially new languages. Right, objects have always we've had object-oriented or object-oriented constructs in languages predating even one of the first object-oriented languages, which is Smalltalk, right? Automated theorem proving concept that predated logic-based languages. The whole concept, essentially, there was this really great treatise. I want to go back up one more of these. When we're talking about object-oriented, there was a treatise on ontology. Ontology is a philosophical study of that which exists, and it describes hierarchies of things, right? Where you have some notion which is the base for all of this. And then if we look at Java or any other object-oriented language, there's usually some base object. Like in Java, it's actually called object. That is the basis from which everything else extends. And so it creates an ontology. So every time you add a new class, you're extending that ontology, describing essentially a tree or graph of objects. And so, I mean, that's been around since, 2,000 years ago, ontology. So it's been around. There's many other connections, right? Programming and programming concepts that we're going to be talking about in this class connect to all sorts of things, right? We get into hardware, computer architecture. We designed high-level languages. Why? Because we wanted better ways to work with, so we didn't have to use assembly. But assembly and the things that we could do was based on the underlying architecture, right? So that was driving what we could do, and inherently drove the evolution of the language. Once we added call stack support, we got recursion. As soon as we added parallel architectures, we gained parallel languages. When we created the internet, well, several years after we created the internet, Java emerged, right? And so there's also, as you'll learn when you're taking the course, the theory course, that there's a theory of formal languages, right? That gets into things like finite state automata, regular grammars, which is the basis for the lexical structure of programming languages, how a scanner and a compiler actually works. Then you get into context-free grammars, push-down automata, which is the phrase level structure of programming languages. These are the underlying formal concepts that allow us to actually create a parser and a compiler. And finally, you'll get into a concept called a Turing machine. And Turing machine basically is a way that we can evaluate, and what we can do is we can actually evaluate the Turing equivalence of programming languages. That the Turing equivalence basically is talking about how we have every language has different strengths, but fundamentally they all have the same power, right? This is why we call them general purpose languages, and I alluded to this earlier. Essentially, any type of problem that we can solve in Java is the same as any type of problem we can solve in Fortran, is the same as any type of problem we can solve in C, on and on, ad infinitum, right? But they interestingly also have the same power as various mathematical models of computation. For example, what you'll learn about is called the Turing machine, or which is equivalent to the lambda calculus. So, and those latter two things got us into what's called the Church-Turing thesis. Alonzo Church came up with the lambda calculus to describe models as a model of computation, while Alan Turing came up with the Turing machine. And they came up with about the same time. That became the Church-Turing thesis, which is what computability means, right? If it's computable, then it's described by the Church-Turing thesis. And you'll learn all about that coming up here, probably halfway through the semester in the theory course. Finally, getting all this down, right? So we talked about all these different great things. The amazing variety of languages, the odd controversies, the intriguing evolution, blah, blah, blah. The whole thing is that all of this is the reason why we want to take this course, why we want to study languages, right? Not only do you need to understand the different concepts of these different languages, but how we can actually utilize and think in a language, right? Every time we pick up a new language, it's changing our way of thinking. It's giving us new ideas, new ways to solve problems. And it also gives us and as it says at the bottom here, unfortunately we're actually learning 4 languages, not 3. But the book will only cover 3 of them. So that's the other part about this course, is we're going to be learning all sorts of new languages in an interesting way, probably different from almost any other course you'll take in computer science. All right, that's all I had for the day. I look forward to seeing you all